Okay, so you should know about different searching techniques, such as a binary search, linear search. So let's talk about how we can use hashing. So I'm going to draw an array really quickly. When I mean quickly, I mean like rapid. Look at the speed. Now, I'm going to number these 1, 2, 3, 4, 5, 6, 7. Now, when we talk about hashing, it uses what we call keys. And let's say that if we're going to talk about number 3, it will store the number 3. If we want to store the number 7, we'll store it in number 7 there. If we want to store the value of 1, we'll store it in here. And the way it searches for information is, imagine you've got a screen. You type in a number, I'm going to search for the number 3. It'll go to key number 3 and find it in there, which is absolutely rapid compared to all the other types of searches you've come across. If we want to search for the number 7, just type in 7 here and boom, it accesses it directly, the value. Now, what happens if we have an array which has got 50 keys or positions? So let's make it a bit bigger, dot dot. Let's imagine it goes all the way up to 50. Now, how many items do we have inside our array? Well, we've got 1, we've got 2, we've got 3, we've got 4. So we're going from 1 to 50 and we've only got 4 items in the array. I hope you can see from a memory perspective, and we've got a lot of wasted space. We don't need this, we don't need this, we don't need this, we don't need this, we don't need 8, 9, 10, 11, etc. So hashing does have its issues in terms of memory wastage. So let's have a look at this in a little bit more detail. So what we have is a hash table, and we have our key space. So we've got 3, 1, 6. These are our values. Now, in order for this to work, we're going to use this algorithm, which is hx equals x. And what that's going to do is basically map these keys to the array. So if we did hx being 3 equals 3, that's basically going to put that into here. hx1 equals x, hx6 equals x, and we've mapped it. But we're still going to have the same issue. For example, if we have 50, we're going to have a hash table with the size of 50. I can't draw 50 on here because I haven't got enough room. But the point being made that we're going to have lots of empty spaces. Wastage. And what we have here is a function which is using a one-to-one in respect to its relationship. h3 goes to 3. So what we need is a different, slightly modified algorithm for this hash table to be more effective. So what I've done is I've made the hash table slightly bigger. We've got 10 items in it, or shall I say 10 positions. And I'm going to change the formula we're going to use for hash. Well, we have a mod and then the size of our table. So in this case, our size is 10. So we're going to mod whatever number we're going to pick by 10, by the size. Okay, so let's take 3 to start with, nice and easy. So we're going to do 3 mod 10, which is actually going to give us 3. So we put it in there. If we did 1, so 1 mod 10 is 1. What about if we did 13? So 13 mod 10 equals 3. Uh-oh, we've already got a 3 in here. So by changing this algorithm, by doing a mod, no longer do we have a one-to-one relationship whereby whatever number we enter as our key, no longer will it put it in that space. We've got the possibility that another number could also need to be allocated the same space, such as 13 in this example, and 3 in this example. So what we have at the moment is a collision, and that is a negative of using hashing in terms of using the mod algorithm. So we are using this mod part of the algorithm to save space. As beforehand, what we would do is we'll put the 13, we'll extend the hash table, and we would have put it in here in that one-to-one relationship. But we're wasting space. So by using this modified algorithm, we're going to be saving space, but at the risk of a collision where we've got two keys wanting to go into the same value. Not cool. And there are different ways we could resolve this. There are different algorithms which could be done. So we've got a collision, check. Now what do we have to do? One of these ways is called chaining. This is not what we're going to be looking at. Another way is using a linear probe. This is what we're going to be looking at. So if we were to go in order, putting these elements in, we would have 3, 1, 6, and 13. Uh-oh, collision. So with linear probing, what we do is we find, so we start here where the collision is, and we search for the next free space. Is there a free space here? Yep. So let's put it in here. And that is linear probe. So this will look at like as a formula. If I did this, so I'm not very good with this pen yet. So h x equals h of x plus f of I mod the size. So the I will basically be incremented starting 0, and it'll increment, well, wherever you're starting on for your hash table, and it'll increment like an I in a for loop. So let's take this beautiful example again. I've done 3, I've done 1, I've done 6, I've mapped it. I've also added 4. We're now doing 13. So h of x mod size, uh-oh, collision. So what we want to be doing next is using this formula here, where we've got 13, I starting at, we'll start at 1. In fact, we'll start at 0, so really we'll be using this formula the whole time. So if we use this formula the whole time, hx blah 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 blah, it'll go as 13. So it'll go as 3. We'll check here. Uh-oh, collision. Not cool. We run this formula again. 13, I becomes 1. Uh-oh. Another collision. I increment by 1. 13, 2, 13, 2, 15, mod, gives us 5, and that's where we're going to put the 13. So this formula here will give us, and well, basically we deal with the collision by doing a linear probe. So no longer are we going to be using this as our formula. This will be our formula.